Then I want to end this chapter by talking about some of the terminologies we will use, and people might use different ones, or people might see these terminologies more ambiguous. So I want to make sure we all understand what we are talking here. So the first one is gene substitution. It's very strange people use genes, as in the very first lecture I talked about alleles, right? Remember, we want to define what is allele, and I told you quite often when we ask students in the class, and people have sort of like a unclear definition for alleles. And part of the reason is people use those terminology not really like stay with its original definition. And here is the an example. When some population geneticists, they use gene substitution, actually are talking about a particular substitution, but it's not really a gene. It's an allele or a variance in the population. So that's something I want to make clear. But since the terminology has been used in several literatures, so you will see that quite often. As I say, in some paper, people will say we sequence 10 genes of the ADH locus. Actually, what they mean is they sequence 10 alleles of the ADH gene. So that's something people might use, and it makes it more confusing, but I just want to make it clear. The definition of allele is an variance of a particular gene or particular locus, and that definition is true for everyone, but some people misuse the gene and alleles interchangeably, and I want all of us won't use that confusing terminology. So when we talk about gene substitution, actually I want to emphasize in the second word, substitution. So when we say substitution, means it's complete replacement of a variance. So showing here is just a simple diagram. We use this diagram for showing the positive selection. But I want to use the similar diagram here to showing the B allele or the B nucleotide, although there's no B nucleotide, but it just there's a variant here. So a new mutation. I just use B as an example. The mutation B arose in the population, then it spreads through the population. After a certain time period, the B is fixed in the population. In this process, we say B is the new substitution of the A. So that's the substitution. So when we use substitution, that means the complete replacement of that particular allele or particular site. Because at a DNA sequence level, sometimes we look at particular nucleotide and talk about the substitution rate, and which we'll use a lot from like chapter 3. So this is something I want to make a clear definition here. Since we will be talking about the complete replacement, and actually that is something about fixation. So B, as showing in the previous slide, B is fixed at the end. B is fixed in the population. So we start population with every individual carry the A allele, then the new mutation B replaced A at the final stage. And that type of a substitution is a fixation process for the new mutation. In previous slide, it's the B like a B alleles replace the A and become the common allele in the final population. So when we want to talk about a particular allele, the probability of the fixation of a particular allele, that's what we concerning here about the fixation time. As mentioned in this slide, the fixation time usually depends on its original frequency. So when we say original frequency, I just want to remind you, if a population, a diploid population, we have n individual, then the allele number, the total number of alleles is 2 times n, right? Any new mutation occurred in the population, the frequency, the initial frequency will be 1 over 2n. So that's the initial frequency of any given new mutation. Then the second part is the property of the new alleles, whether there's a selection involved. So it's a negative selection or positive selection, or it's neutral. So as I say, natural selection is not operating in overall the genome. Selection is really effective in certain part of the genome if the gene has a phenotype, and the variation in the population will contribute, will showing like in differences in reproduction or survival. And that's the one we are concerning about, the selection. We're operating in those variants. But an allele could be neutral. That means it's fluctuating in the population by chance. And we already talked about that earlier in this chapter. Then the third one is the population size we just mentioned in the beginning of this class. So the fixation time or the fixation probability is basically affected by these 3 confounding factors. And I have a formula right here. Just try to put everything together, considering about the initial frequency and the population size, effective population size, and whether there's a selective constraint showing by the S parameter. And that's the probability we can consider, and this was mentioned first by Kimura in 1962. So if we look at this formula, I just want to remind you one thing from your like elementary calculus. So we can try to approximate, because the formula looks like a little bit complex, but you can sort of like approximate it to a number which we can explain or we can look at more clearly. So the approximation we use is this formula. So this is from your like I think high school or like the freshman calculus. So you learn like we can approximate e to the power of next minus x, and it will be equal to 1 minus x if the x is very small. So that's like there's a assumption. If x is very small, and this one, we can approximate this formula to 1 minus x. So that's the thing you can put into the formula, and you can make a very simple approximation to look at the probability. So the probability of fixation, or we say the fixation probability, will be equal to the initial frequency of the allele, and that's 1 over 2n. So this becomes a very simple approximation, tells you at the bottom of this slide is for any given neutral mutations, because we already explained to you the frequency of the new mutation is 1 over 2n. Then the probability of the fixation of this new mutation is equal to its initial frequency, and showing here P, that's the probability, the big P is the probability, equal to 1 over 2n. Okay, but that's for neutral mutation, and then that is something very important. But if S is not equal to 0, it means there's a selection involved in the process. Then we have to like live with the selection coefficient showing us the small s here. Then we'll say, okay, the population size, and usually we're concerning about the effective population size, and we still can make approximation that's showing at the bottom of this slide. So if we do the approximation and just assuming the ACE is a positive number, so if S is larger than 0, but it's very, very small. Then we can look at this formula and calculate if a positive value of S is true and the population size is large. So there are several assumptions to make this approximation. If that is true, then P is equal or approximate the fixation probability is equals to 2 times the selection coefficient. So all this approximation looks probably not accurate for a mathematical point of view. So if you look at your friends in the Department of Mathematics, they say, why you're like always make an approximation? Because they like a clean formula, like a real number. But all this we do is the approximation. So we make assumptions, then we say, okay, approximately what would be the number. But the beauty of this approximation is you can make the formula really simple and you could understand what exactly it means, or at least you know which parameter will contribute to the final results. For example, here is the fixation probability. So if a neutral allele, let me repeat again, if a neutral allele without any selection, then the fixation probability equals to approximately equal to its initial frequency. And if there's a selection involved in the population for given positive value of the selection coefficient, and we can approximately to calculate the fixation probability equal to 2 times of the selection coefficient. So it's just like all this approximation make the formula much easier, and you know which parameter will contribute to the final result more effectively. Except the fixation probability, another thing we are more concerning is about the fixation time. It's like how long will it take for a new mutation fixed in the population? And that's what we mean by fixation time. So as I showed you in a couple slides before, the B allele replaced the A, and I just use an arrow to say, okay, give a certain time point after certain, like a long period of time, and B allele replace the A, and it populates the entire population. In population genetics, we want to know how long will it take. If a neutral allele, that means there's no selection involved, how long will it take for a new mutation like if the mutation going to fix, because there's a probability a lot of times the mutation won't fix in the population. But if this mutation has a chance to be fixed in the population, how long will it take? And the simple answer for that is it would take 4n generations. So you don't have to memorize it, but just give you some idea about it's related to the organism's generation time. So it takes a 4n generation for neutral allele to be fixed in the population. And this is a simple diagram I rewrote from your textbook, and you can see this type of diagram in a lot of different textbook or review papers, because we are trying to explain very similar things. Showing here is like the mutations occur in the population. And on the top panel is showing the neutral mutations. So this is just try to illustrate like what exactly looks in the population. So in every line, the starting point is the 1/2n, and you can you can see the allele arose in the population and increase the frequency, but fluctuating in the population a little bit, then sometimes, and most of the time, they go down to 0. Means a lot of those neutral mutations actually they don't have a chance to be fixed in the population. So they become allele at a lower frequency, and sometimes even they rise in the intermediate frequency, but then they lost in the population. So that was showing in the diagram that all the lines going down to the 0. And occasionally, every once in a while, you have a neutral mutation which fluctuating in the population but gradually increase in its frequency to the final stage, the fixation. And the time period for that fixation is showing here by T, and in the previous slide I already told you it will take 4n generations for a neutral mutation to be fixed in the population. So that's in the top diagram to show this process. So that's for neutral mutations. For advantageous mutation, there's a selection push its frequency. So to just simply show this, that those alleles will have much shorter time for fixation. So the same thing, I would say, from the initial frequency 1/2n to its final fixation, that's 100% of the population have this or carries this particular mutation. Then that's the fixation. And the fixation time for this advantageous mutation are very, very short. So those two, some paper or textbook will put the two together, but we're trying to show very similar message, just to contrast the differences in fixation time between the neutral allele and the advantageous alleles. So that's showing here. Then another thing is the rate of gene substitution, and which we're going to talk for the entire chapter 3. We're talking about the substitution rate. And here is the same thing. We want to show you the neutral mutations. And this is the famous Kimura's formula, because we just say if an allele is going to be fixed or has a chance to be fixed in the population, and the probability is 1/2n, right? Fixation probability is 1/2n. Then you ask how many mutations can arise in the population at the given generation. And that is very simple, because you have n alleles or NE as the population size, and every individual carry 2 alleles. We just assume all diploid. Ignore the X and Y, sorry. Then we say, okay, any given mutation, that's the mutation rate, mu. Right. So that's the beginning of this formula. K is the substitution rate, equal to 2n mu. So n is the population size, mu is the mutation rate. So this part is talking about how many mutations will be produced for a given generation. Then if you have this amount of mutation, then we will calculate how many of this, or what's the probability of the fixation for the given amount of mutations. So for any given one is 1/2n. That's the fixation probability. So we times the total number of mutations, 2n mu, then multiply by its fixation probability, that's 1/2n. Then it's very simple calculation we learned probably from, I don't want to say elementary, but it's probably in the high school, junior high, we already know how to do this calculation. So it makes the formula become really, really simple. The substitution rate, K, is equal to mutation rate. So that's the formula showing here. So K, the N, is equal to mu. And that's the neutral mutation rate contribute to the substitutions. If it's advantageous mutation, then that we'd have to consider the selection coefficient. So we put the selection coefficient to the formula, then it becomes 4ns mu, and that's the what we say the substitution rate of a given advantageous alleles or advantageous mutations.